All right, let's look at 1A. So these are obviously really high point value questions. On the test, it will be broken down into a multi-step problem. So I would kind of say part A, do this, part B, do this. Kind of like I have lined out here. So part A is a domain. Okay, domain and asymptotes, the vertical asymptotes, are very closely related. What makes the bottom equal 0? So my domain x cannot be plus or minus 1. If you did an interval, that's negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. B, the x-intercept is when your y equals 0. So if we plug in 0 for our y, we just get 0. Y-intercept, plug in 0 for your x's, and you get 0. I told you you could skip symmetry. Asymptotes. So vertical asymptotes are x equals the things x couldn't be in the domain. So x equals 1, x equals negative 1. How did I have you find the horizontal? Limit x approaches plus or minus infinity of 2x squared minus 1. So if we divide everything by the highest power of x, so we'll take everything times 1 over x squared. So we get 2 over 1 minus 1 over x squared. And this is helpful because anytime you have a number over infinity, that turns into 0, so we get 2. So the horizontal is y equals 2. E, increasing, decreasing. So how do we find increasing and decreasing? What do we have to do? Yep, we need the sign line for the derivative. So it's a fraction, so you have to do quotient rule. Low, d high, minus high, d low, over low, squared. So we get 4x cubed minus 4x minus 4x cubed. So negative 4x over x squared minus 1 squared. Now critical points are anywhere the derivative is 0 or undefined. If we're looking at a fraction, it's really like saying what makes the top 0, what makes the bottom 0. So what makes the top 0?
0.
And the bottom?
Positive 1, negative.
Okay. So when we do our sign line, those are the 3 numbers we have to use. And then we do our test points. Okay, so if I put in negative 2, the top is positive, the bottom's positive no matter what. So that's positive. Then this is also positive, 1/2 is negative, after 1 is negative. So my graph is increasing where it's positive. I cannot just say negative infinity to 0. Why? There's a vertical asymptote, so we have to break it up. Negative infinity to negative 1, union negative 1 to 0. Decreasing, 0 to 1, union 1 to infinity. All right, F, I asked for max and min. So we look at this. The only switch right here at 0, it went from increasing to decreasing, so that would be a local max. You need the ordered pair to actually graph it. So if you plug in 0, you get out 0. There is no min on this one. Inflection points. What do we need? Second derivative. So that's low, d high, minus high, low, so 2 comes down, inside stays the same, subtract 1 from the power, times derivative of the inside, over low, squared, so we come to the 4th. Now we can cancel an x squared minus 1 out of everything, so that leaves us 3 of them on the bottom. So we get negative 4x squared plus 4. Here, minus a negative, so plus 4 times 2 times 2x, 16x squared. So we get 12x squared plus 4 over x squared minus 1 cubed. Inflection points are anywhere the second derivative is 0 or undefined. So if you set, it's again just really top and bottom equal to 0, if we set the top equal to 0, what happens? You get 9. We can't use that. So it's really just what makes the bottom 0, which is plus and minus 1. Are those going to be actual points we plot on our graph? No, because we already know what happens at positive and negative 1. There's asymptotes there. So it's just saying we don't have a true inflection point. It's just changing concavity on each side of the asymptote. So the concavity. We do our sine line. Plug these into the second derivative. So the top is always positive. The bottom, I put in negative 2, that's positive. If I put in 0, that's negative, and 2 is positive. So our graph is concave up, negative infinity to negative 1, union 1 to infinity. Concave down from negative 1 to 1. And then I want you to graph it. Now, when you graph these things, I expect you to plot all the stuff we found. So x and y intercepts were both at 0. Vertical asymptotes at positive 1 and negative 1. So now we draw those in dashed. Horizontal asymptote was at 2. Inflection points, if you do have true points, you need to find their y values so you can mark them on your graph. And then how did we mark those? With x's. Our only max and min was at 0, 0. So this is what we have. So we look back. Our graph starts out concave up, so it's curved upward. So your options for curved upward, it could look like this, or it could look like this, right? Depending on if you're increasing or decreasing. If we look, we need to start out increasing and curved upward. It has to look like this. We know asymptotes, we should be getting closer to those. Then we are concave down between negative 1 and 1. So concave down, if it's increasing, would look like this. Decreasing would look like that. And our graph is increasing. So curved downward, but increasing until we get to 0. And then after 0, it's decreasing, but still curved downward. And then finally, we are concave up and decreasing. So the final piece looks something like that. Just excuse the part where I kind of ran into my asymptote there. I got lazy and didn't want to redraw. So, is that one okay?
Yes.
All right. Let's look at the next one. So B, probably the part that made this a little bit harder was how it was written. In that, when you do the derivative of this, what do you have to do? The product rule. So we have to kind of adjust and make sure we're working that out here. So if I look at this, first thing was domain. Is there anything this can't be? It's a polynomial. So my domain is just negative infinity to positive infinity. And we also know if it's a polynomial, there are no asymptotes. X-intercept, if you plug in 0 for y, then we get 0, -2. Y-intercept, if we plug in 0 for x, we get 0. Are we okay on those? So asymptotes we already said. There are none. So then we need the increasing, decreasing. So we need our derivative. So practical derivative of the first is 1 times the second plus the first times derivative of the second. So 3 comes down, inside stays the same, subtract 1 from the power, times the derivative of the inside, which is just 1. So if you notice, we have two terms. What do both of them have? If I take that out, I'm left with an x plus 2 in the first term, and a 3x in the second term. So we get x plus 2 times 4x plus 2. Alright, so critical points. This is never undefined, but what makes it 0? So if you set x plus 2 equal to 0, you get
I'm just kidding.
so if I set the x plus 2 equal to 0, we get a 2. If you set 4x plus 2 equal to 0, we get -1/2. So then we need increasing, decreasing. So we make our sign line. And then -3, this would be positive. -1 is negative, 0 is positive. So we're increasing, -infinity to -2. Yeah.
So when you put x plus 2 there, 4x plus 2 there, should the square still be there? Or did you get rid of it?
Oh, did I drop my square? I
Oh,
did. Thank you.
I was just-
Let's see. Does that change anything? It does. Yeah, it's just gonna flip those signs. Thank you. I was just making sure you're paying attention. Bo passed, the rest of you failed.
Yay.
Alright, so if we put in a -3, that's a negative now. If we put in -1, that's also negative. And if we put in a 0, that's positive. So this time, can I just say that we are decreasing from -infinity to -1/2? Yes, because it's not an asymptote at -2. You alright?
Yep.
Did I make another mistake? Okay. So we've got our increasing, decreasing. Now we can do max and min. So, if you are decreasing and switch to increasing, what happens? Max or min? Min. X is -1/2. To get the y, you plug -1/2 into what we started with. And for the sake of time, I'm just going to tell you that was -27/16. Alright, then we need inflection points, so second derivative. So we're going to do practical again. So derivative of the first, so the 2 comes down, inside stays the same, subtract 1 from the power, so it's now to the first, derivative of the inside is just 1, so that's the derivative of the first times the second, plus the first, derivative of the second is 4. So we could take out an x plus 2, and that leaves us with 2, and 4x plus 2, and 4 times x plus 2. we get 12x plus 4 that's 12. Alright, so inflection points are anywhere second derivative is 0 or undefined. It's never undefined. If you set each of these parentheses equal to 0, you get -2 and -1. Did you find out where you went wrong? Then we can do our concavity. So put in -3, negative times negative is positive. Negative 1.5, so positive times negative is negative. 0 is positive. So we're concave up. Negative infinity to -2. Union -1 to infinity. Concave down. -2 to -1. And then graph. On this, so we don't have any asymptotes to worry about. Intercepts at 0 and -2. We had our minimum at -1/2, -27/16, which is like not quite -2. Inflection points. This is a problem that I've noticed on a few of you. You're not getting the actual points. Since these aren't asymptotes, we need the order pairs. So to get the order pair, you plug it into the beginning. So if we put in a -2, what do we get? 0. So -2, 0 is an inflection point. So I marked that with an X. I already have a point there too. And the other one, if I put in -1 to the original, you get -1. Alright, so my graph. Until I get to this point, it's curved upward, concave up, and we know it is decreasing. So decreasing, but curved upward. Whoops, that's my mark there. Okay, we have to keep decreasing until we get down to our min, but we're going to be curved upward just slightly here in the middle. Then we're back to being curved upward for the rest of the time, so we come down, hit our min, and we switch to increasing, and so it looks something like this. I apologize, I know my graph is a little rough. Alright. So those are definitely your high point value questions. Let's go to problem number 8. So, roles and mean value theorem. You have to check your criteria. And you have to give me enough that I actually believe you know what the criteria is. So you can't just say meets the criteria. Okay, that's not going to cut it. You have to give me something. So, Rolle's theorem actually had 3 conditions. The first condition is it had to be continuous on the entire interval. So if I look at problem 8, that's a polynomial. So it had to be continuous on the closed interval. And that was 1 to 3. Technically this is continuous everywhere, but the condition, it had to be from 1 to 3. Second thing, it has to be differentiable. Now if it's not a polynomial, you actually have to do the derivative and see, where does this derivative not exist? Is that in my interval? Since this is a polynomial, it is differentiable. And it only has to be differentiable on the open interval. So in other words, if the derivative doesn't exist at the endpoint, that's okay. Third criteria, the endpoints have to be equal. So if I put in a 1, I get -4. If you put in a 3, you get -4. On a Rolle's theorem, this is where the bulk of your points are going to come from. So if you're not showing me the criteria, you've just missed over half the problem right there. Okay, make sure you're clearly stating all three. Then,
So those are when you plug in your endpoints to the original. Okay.
and they have to be the same for Rolle's theorem. Then what Rolle's theorem tells us is somewhere the derivative is 0. So we do our derivative, which would be -12 plus 6x, and it has to be 0. So x is 2. You might get multiple answers. We only want the ones on this interval. So if I got 2 and -2, 2 is the only one I would use. The Rolle's theorem tells us some number between 1 and 3 has to make the derivative 0. So the number that worked here was +2. Is that okay? You guys have modified your papers and clearly shown yourself what I expect to see.
So if I say for criteria, polynomial equals differentiable and continuous,
That's
that's
fine.
fine.
Yes.
Okay.
I am writing these about you. I'm actually replying to an email and saying my slate is working so far.
Oh, good, good.
So now it's going to break.
For sure.
All right, now we have the mean value theorem. So again, first thing is criteria. A mean value theorem is a more generic version. Rolle's theorem is like a special case. Mean value theorem only has 2 criteria, continuous and differentiable. So again, it's a polynomial. So it has to be continuous everywhere. More specifically, the interval we need is -2 to 2. Second, it has to be differentiable in the open interval. So because it's a polynomial, it is differentiable everywhere, more specifically from -2 to 2.
Ooh.
Then, what the mean value theorem tells us is the derivative equals the slope between the endpoints. So we need the endpoints. So if we put in -2, we get -8 plus 6 plus 2, which gives us 0. And if we put in a 2, we get 8 minus 6 plus 2 is 4. So the slope between these, y sub 2 minus y sub 1 over x sub 2 minus x sub 1, we get 4 over 4 is 1. So the derivative is going to be equal to 1 somewhere on that interval. So my derivative is 3x squared minus 3, I need that to equal 1. So x squared equals 4/3. Square root plus and minus, you get 2 over the square root of 3, so 2 radical 3 over 3. You have to verify both of those do fall between -2 and 2. So those are the numbers. Mean value theorem and Rolle's theorem weren't hard, but you do need to go back and refresh what they said, how to use them, and what the criteria are. All right, is that good? Let's go to 13. All right, does there exist a function such that did I adjust yours to say polynomial function?
Yeah.
Good. All right, so f of 0 equals -1. F of 2 equals 4. And the derivative is less than or equal to 2 for all of x. Okay, we had this one as like a bonus question on a quiz. We did it in our notes one time. What I'm wanting you to do is make a connection here. I told you this is a polynomial. So you know it is differentiable and continuous, right? So that means mean value theorem must work. Mean value theorem says if it's continuous and differentiable, somewhere the derivative equals the slope between the endpoints. So let's find the slope between these points. Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. We get 5 over 2, which is 2.5. So can the derivative always be less than or equal to 2? No. By the mean value theorem, somewhere between x equals 0 and x equals 2, the derivative must be 2.5. So it is not possible for the derivative to always be less than 2. Is that okay? So number 14. Our function 1 minus x to the 2/3 power. Alright, so it says, show that f of negative 1 is equal to f of 1. Okay, so if I put in a negative 1, we get 0. If I put in a 1, we get 0. Okay, so that's the third condition of Rolle's theorem. The endpoints are equal. But it's telling us there is not a number in the interval negative 1 to 1 where the derivative is 0. And Rolle's theorem says there must be. And then I said, why does this not contradict Rolle's theorem? So what ideas do you have? I'm telling you Rolle's theorem didn't work here, but why does that not prove Rolle's theorem is wrong?
It's not differentiable.
Okay, let's check. Is this continuous everywhere? Can I do the cube root of anything?
Probably.
Yeah, this is continuous, so the first criteria is met. The third criteria is met. The endpoints are the same. Let's check the second criteria. So we need to see if it's differentiable. So if you do the derivative, you get negative 2 over 3 times the cube root of x. This is not differentiable at 0. And 0 is in between negative 1 and 1, so Rolle's theorem doesn't work. Our criteria wasn't met, so we can't use the theorem. Questions there? Number 15. Okay, I really want to talk about these questions. They are, I'm definitely going to ask you something like this first of all, because I really like these questions and it's really tests if you know the connections between all of them. So you'll notice, this is the graph of the derivative. That is the first important thing you need to recognize. We're not looking at the original function. We are looking at the first derivative. So part A, I want to know where my graph was increasing and decreasing. Now I'm not asking you where the derivative is increasing and decreasing. I'm asking you if the original, where was the original increasing and decreasing? So think about, how do we find increasing and decreasing? We do the derivative, we get our critical points, right? And we figure out those critical points are where that derivative is 0. Can you tell me where the derivative was 0? 1, 3, and 5. So my critical points are 1, 3, and 5. Everybody with me here? Corbin, you with me? Okay, so what you would do on the first page, we found our critical points and we made our sign line to decide increasing and decreasing. So the sign line is where the derivative was positive or negative, right? We would take test points, plug them into the derivative when we were worried about positive or negative. So if I look at my derivative, before 1, was my derivative positive or negative? It was positive. Okay, after 1, my derivative was negative. Between 3 and 5, the derivative was positive. And after that, the derivative was negative. So the graph is increasing when the derivative was positive. So that's negative infinity to 1, union 3 to 5. Decreasing where the derivative was negative. So that's 1 to 3, and 5 to infinity. Second question. Where does the function have a maximum of, yes?
Should it be to the infinities or those points? Because it's not arrows at the end, it's just like actual points.
Oh, I see.
Arrows as well.
Yeah, I guess that's true. I don't have actual arrows. You're right. So not really infinities. 0 to 1, and you could do a bracket. Even it won't matter if you do bracket or parenthesis for increasing, decreasing, and then this, I guess the graph ended at 6. Thank you. All right. So where does it have a max or a min? So if I look at 1, my graph was increasing and switched to decreasing. So that is a local max. Okay, at 3, it was decreasing and switched to increasing. So that is a min. At 5, increasing to decreasing. So that's another max. I didn't ask you which was which, but you could easily identify those. Number 16. All right, so this one told us on part A, if this is the graph of our function, we need to find inflection points. So we're finding inflection points every time. Remember, inflection points are when the second derivative is 0. Okay? If this is the original function, inflection points, the second derivative is 0, that's where the concavity changes. At 2, is my graph curved upward or downward? It's curved down. At 4, it's curved up. So my inflection point had to be somewhere between 2 and 4 because I changed concavity. So, can we agree 3? What would the other one be? And my reason is just the concavity changes. B said, okay, I still want the inflection points, but now pretend this is the graph of the first derivative. Okay, so I'm not just looking at the concavity of this anymore. This is my first derivative. I want to know when the second derivative is 0. So when will the derivative of this be 0? Derivative is the slope of a tangent line. So where does this graph have a horizontal tangent line? And my reason, horizontal tangent. C. Let's say this is the second derivative. So if I'm looking at the second derivative, inflection points are where the second derivative is 0. So where is this graph 0? At 4 and 1 and 7. My reason is just that's where the graph was 0. My personal thought, we're doing pretty good this year. We've only missed a couple days, so we're really not behind right now. I was going to suggest maybe one more day and do our test on Thursday. Would that be okay?
Yeah.
So tomorrow, I have a paper that we're going to go through, and I've kind of recapped. So I think I did this like in chapter 2. I made a little summary sheet for you of kind of the important things. And so I've got one. We'll have mean value theorem, Rolle's theorem, critical points, inflection points, asymptote rules. We'll do some practice with these graphs. So that's my plan tomorrow, just kind of one more day to rehash everything, make sure we know all of our criteria, what's what, and then take our test Thursday. Okay? We have a few minutes right now. I feel like we should work another problem.
I knew you were gonna do that.
Which one would you like for me to work out? Pick one.
No, like, you literally do this.
I don't like wasting time. Are you judging me?
No, you are the only teacher that does this.
Are you
Do you
judging
realize
me?
that?